right. Hello, everybody. Let's get some tunes going on. How's it going? Welcome back in.
Michael says test. Nichildeming says test.
Nice. Alright, doing good. Today is a good day. Alright, everybody, welcome back in. I hope you're having a wonderful day so far. Oh man, can't stop yawning. I am tired. Oh boy. Gotta wake up here, wake up. I need 10 minutes here to kind of wake back up. I took a little power nap. I had an hour here, so I just quickly rested my eyes. And I'm having a hard time opening them back up. Alright. Welcome in, everybody. Hope you're having a wonderful day so far. Today is Monday, May 19th, 2025, and we are back going to be learning today some programming, but more importantly, we're going to be learning some mathematics. We're going to be learning some Calculus 1. So we're going to be going through and starting the Khan Academy Calculus 1 course today. I'm super excited to begin this course and really get into kind of the ins and outs of calculus and kind of have a more in-depth knowledge about mathematics in general. And then more relation into programming with Python and mathematics. So I'm going to be creating a repo here where we'll be taking and completing this course. You can follow along yourself while taking the course if you would like as well, or just by following my repo. So feel free to do either. Okay, let's go ahead and jump on in here. Oh my goodness. My eyes. Independent mathematics. Okay, so let's go ahead. Okay, I've got a new folder here called Independent Mathematics. This will be our study guide here. Let's go like this. Get so we're independent mathematics, so we'll go make Hey, how's it going? I appreciate you for being here. Welcome, Austin. How you doing? Indy. Create. Okay. Let's go. Python.
Fantastic. Hope same for you.
I'm good. Yes. Python 3. Python 3 V and V. Create. Dash M. Okay. So Python 3 dash M, we're gonna V and V. No such files directories. Python 3. There we go. Now we have virtual environment. Now let's go ahead and say git add. We're gonna say git. Or so we'll say touch dot git ignore. We'll put on here, what is the git ignore for V and V? Okay. Git add. So we
Tim
get
says,
touch.
hi Professor, my head is pounding but I'm here for duty.
How's it going? I am tired too, dude. I'm struggling with you. How are you doing? What's going on, Tim? Welcome back in. I am on the struggle bus, let me tell you. I can barely keep my eyes open. This is gonna be a rough intro math session, let me tell you.
Tim says, happy to announce I'm now an Alum Prof.
Am I now in what? Alum Prof.
Primus says, you.
Oh, did you graduate?
Tim says you also have a hangover, Prof. Deming. Primus says, you.
Yo, Primus, how's it going? Did you graduate, Tim? Okay, so we have virtual environment. Let's go here.
Tim says, yes, I graduated. Zozav says, yo, bro.
Hey, how's it going? How's it going? Okay, so I've added these files. Let's go git status. We'll go git add.
Premise says, are you learning AI? Tim says Alan Iverson. Magnet says, calculus. Magnet says, I got a calc final this Thursday.
Nice.
Tim says, are we watching lectures from Sal Khan?
Okay. Okay. All right. We're going to... We have set up a virtual environment. We have a git ignore and a readme. We're going to add in a new dir, so we'll go...
says, held a message for reason, bullying. Bilal will post it to chat. Rishabh says, where's calculus? Endpoint says AOFK.
Hey, Endpoint, how's it going? They thought your message was bullying. They flagged it. So we're just getting our project directory set up. So we're going to be learning and teaching ourselves calculus with using Python as our calculator.
While new project, Michael. Tim says we have automate now.
I guess so. Hey, Jeremy Fuller, welcome back, dude. It's been a while.
Endpoint says out of the office, integrals.
So yeah, we're going to be teaching ourselves the Khan Academy calculus course using Python, and we're going to be tracking it using this GitHub repo so you guys can follow along as well. So I'm going to do this. I'm going to go like this. We're going to make a dir called Khan Academy.
Magnet says automate. Rishabh says first like man.
Thanks for the likes. Yes, if you guys are here, please leave a like. Appreciate you guys so much. So we have Khan Academy. Let's go CD.
Magnet says second like
Khan Academy. Let's go make dir calculus 1.
Tim says let's get Mike to 2,140 likes to AFR.
Let's go.
Endpoint says uses underscores for your directories. I already dig it followed.
What's going on, dude? Thanks for coming in, Endpoint. So we're just taking a quick break from our normal project learning, right? So Mondays are going to be the days where we're going to study mathematics. I know, like, my philosophy with this is a lot of people shy away from mathematics, especially with programming. So I kind of want to be the opposite. I want to be the guy that kind of gains an expertise or knowledge in mathematics so I can kind of incorporate these like appropriately into programming with Python and be able to use, you know, these various functions and whatnot appropriately and, you know, confidently as well. So I do want to, you know, I've also had just a personal goal of just being better at math. Math is kind of like the keys to the universe. So I just really appreciate yeah, so I appreciate everybody being here and joining along. So let's go ahead. We have calculus 1 here. So let's go. Okay, now we're in Khan Academy's calculus 1 directory here. So let's go git add. So we'll have to make dir again, and this will be, so let's go over to the Khan Academy calculus 1. Unit 1. Calculus 1, Unit 1. Okay, let's CD Calculus 1, Unit 1. Okay, here we are. Now let's go get add. We'll say touch. We'll say calculus 1 unit 1 notes.md. I'm not sure why I did capitals.
Endpoint says, are you going to model a cell anytime soon?
All right. Cool. Just got that set up. All right. Calculus 1 notes here. All right. And then let's go get add all, get commit. Start the Khan Academy Calculus 1. Okay, here we go. Oh boy.
Tim says, Mike, you need a fresh summer cut.
I know I need to get a haircut. Y'all's been telling me. I'll have to get one quick here soon. All right, you guys. Thanks so much for joining me here. We are going to be taking a stab at Khan Academy's Unit 1 here for Calculus 1. I'm super excited to get into this and to learn more and to use Python more specifically to learn these various, inner workings or whatnot. So I appreciate you guys being here and joining me for this. I'm going to go ahead and before we go ahead, I'm going to go ahead and fill up my drink with some lemonade or maybe some Coke. We'll see. Go ahead and get yourself a snack, get yourself a drink, and we're going to get into the lectures here shortly. So this is Limits Intro. This is going to be our first unit video here. So I'll be right back. We're going to get into this.
Tim says, bro, preparing like he's about to go to war.
All right. Yeah, preparing for war here. Pretty much. It's pretty much what we're doing here. Okay.
Eduardo says, good evening.
Hey, how's it going? Oh, I got hair. There we go. Cat hair. Hey, Eduardo, how's it going? All right, you guys. Let's go ahead, without further ado, get into this lesson on Calculus 1 on limits. This is the Unit 1, Lesson 1. I'm excited to get started here. So in this video, we learn about limits, a fundamental concept in calculus. Limits help us understand what a function approaches as the input gets closer to a certain value, even when the function is undefined at that point. The video demonstrates this concept using two different examples with different functions created by Sal Khan. Okay.
is a super important idea. It's really the
Tim
idea that
says
all of
Biochemist
calculus
learns
is
math.
based
Please
upon.
pray.
But despite being so super important, it's actually a really, 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 really simple idea. So let me draw a function here. Actually, let me define a function here. A kind of a simple function. So let's define f of x. Let's say that f of x is going to be x minus 1 over x minus 1. And you might say, hey, Sal, look, I have the same thing in the numerator and the denominator. If I have something divided by itself, that would just be equal to 1. Can't I just simplify this to f of x equals 1? And I would say, well,
Ho says
you're
would be better to
almost
go
true. The difference between
1.25 or
f of
1.
x equals 1 and this thing right over here is that this thing can never this thing is undefined when x is equal to 1. Because if you set, let me define it right, let me write it over here. If you have f of, sorry, not f of 0, if you have f of 1, what happens? In the numerator, you get 1 minus 1, which is, let me just write it down. In the numerator, you get 0. And in the denominator, you get 1 minus 1, which is also 0. And so anything divided by 0, including 0 divided by 0, this is undefined.
Undefined.
This is undefined. So you can make the simplification. You can say that this is the same thing as f of x is equal to 1, but you would have to add the constraint that
That's gonna be
x
0.
cannot be
Be
equal to
1.
1. Now this and this are equivalent. Both of these are going to be equal to 1 for all other x's other than 1, but at x equals 1, it becomes undefined. This is undefined and this one's undefined. So how would I graph this function? So let me graph it. So that is my y is equal to f of x axis. Y is equal to f of x axis. And then this over here is my x axis. X axis. And then let's say that this is the point x is equal to 1. This over here would be x is equal to negative 1. This is y is equal to 1. Right up there, I could do negative 1, but that won't matter much relative to this function right over here. And let me graph it. So it's essentially, for any x other than 1, f of x is going to be equal to 1. So it's going to look like this. It's going to look like this. Except at 1. At 1, f of x is undefined. So I'm going to put a little bit of a gap right over here. The circle to signify that this function is not defined. We don't know what this function equals at 1. We never defined it. This definition of the function doesn't tell us what to do with 1. It's literally undefined when x is equal to 1. So this is the function right over here. And so once again, if someone were to ask you what is f of 1, you'd go, and let's say that even if this was a function definition, you'd go, okay, x is equal to 1. Oh wait, there's a gap in my function over here. It is undefined. So let me write it again. It's kind of redundant, but I'll rewrite it. F of 1 is undefined. But what if I were to ask you, what is the function approaching as x equals 1? Now this is starting to touch on the idea of a limit. So as x gets closer and closer to 1, so as we get closer and closer x's to 1, as we get closer and closer x's to 1, what is the function approaching? Well, this entire
It's
time, the
punching the
function, what's it getting
undefined.
closer and closer to? On the
The
left-hand side, no
undefined
matter how
value.
close you get to 1, as long as you're not at 1, you're actually at f of x is equal to 1. Over here, from the right-hand side, you get the same thing. So you could say, and we'll get more and more familiar with this idea as we do more examples, that the limit as x, and lim, short for limit, as x approaches 1, of f of x is equal to, as we get closer, we can get infinitely close to 1, as long as we're not at 1, and our function is going to be equal to 1. It's getting closer and closer and closer to 1. It's actually at 1 the entire time. So in this case, we could say the limit as x approaches 1 of f of x is 1. So once again, has very fancy notation, but it's just saying, look, what is a function approaching as x gets closer and closer to 1? Let me do another example where we're dealing with a curve, just so that you have the general idea. So let's say that I have the function f of x, and let me just for the sake of variety, let me call it g of x. Let's say that we have g of x is equal to, I could define it this way. We could define it as x squared when x does not equal, I don't know, when x does not equal 2. And let's say that when x equals 2, it is equal to 1. So once again, kind of an interesting function that, as you'll see, is not fully continuous. It has a discontinuity. But let me graph it. So this is my y equals f of x axis. This is my x axis right over here. Let me draw x equals 2. Let's say this is x equals 1. This is x equals 2. This is negative 1. This is negative 2. And then let me draw. So everywhere except x equals 2, it's equal to x squared. So let me draw it like this. So it's going to be a parabola. It'll look something like this. It's going to look something, let me draw a better version of the parabola. So it'll look something like this. It looks something like this. Not the most beautifully drawn parabola in the history of drawing parabolas, but I think it'll give you the idea. I think you know what a parabola looks like. Hopefully, it should be symmetric. Let me redraw it because that's kind of ugly. Okay, so that's looking better. Okay, all right, there you go. All right, now this would be the graph of just x squared, but this can't. It's not x squared when x is equal to 2. So once again, when x is equal to 2, we should have a little bit of a discontinuity here. So I'll draw a gap right over there. Because when x equals 2, the function is equal to 1. When x is equal to 2, so let's say that, and I'm not doing them on the same scale, but let's say that, so this, on the graph of f of x is equal to x squared, this would be 4, this would be 2, this would be 1, this would be 3. So when x is equal to 2, our function is equal to 1. So when x is equal to 2, our function is equal to 1. So this is a bit of a bizarre function, but we can define it this way. You can define a function however you like to define it. And so notice, it's just like the graph of of f of x is equal to x squared, except when you get to 2, it has this gap.
Hey, Guild of
Because
Intriguing.
you don't use the f of x is equal to x squared when x is equal to 2. You use f of x, or I should say g of x. You use g of x is equal to 1. Have I been saying f of x? I apologize for that. You use g of x is equal to 1. So then at 2, just exactly at 2, it drops down to 1, and then it keeps going along the function g of x is equal to, or I should say, along the function x squared.
You approach
So my
this,
question
and
to you, so there's a couple of things. If I were to just evaluate the function g of 2, well, you look at this definition. Okay, when x equals 2, I use this situation right over here, and it tells me it's going to be equal to 1. But let me ask a more interesting question, or perhaps a more interesting question. What is the limit as x approaches 2 of g of x? Once again, fancy notation, but it's asking something pretty simple. It's saying as x gets closer and closer to 2, as you get closer and closer, and this isn't a rigorous definition, we'll do that in future videos. As x gets closer and closer to 2, what is g of x approaching? So if you get to 1.9, and then 1.999, and then 1.99999, and then 1.9999999, what is g of x approaching? And or if you were to go from the positive direction, if you were to say 2.1, what's g of 2.1? What's g of 2.01? What's g of 2.001? What is that approaching as we get closer and closer to it? And you can see it visually just by drawing the graph. As g gets closer and closer to 2, and if we were to follow it along the graph, we see that we are approaching 4. Even though that's not where the function is, the function drops down to 1, the limit of g of x as x approaches 2 is equal to 4. And you can even do this numerically using a calculator. And let me do that, because I think that will be interesting. So let me get a calculator out. Let me get my trusty
Okay, so you just follow
out.
with the main function. The limit goes to where that gap actually is.
You can numerically say, okay, what's it going to approach as you approach x equals 2? So let's try 1.9. For x is equal to 1.9, you would use this top clause right over here. So you'd have 1.9 squared. And so you'd get 3.61. Well, what if you get even closer to 2? So 1.99. And once again, let me square that. Well, now I'm at 3.96. Well, what if I do 1.999? 999. And I square that. And I square that. I'm getting a 3.996. Notice, I'm getting closer and closer and closer to our point. And if I got really close, 1.999999999 squared, what am I going to get to? It's not actually going to be exactly 4. This calculator just rounded things up. It's going to get to a number really close to 4. And we can do something from the positive direction too. And it actually has to be the same number when we approach from the below what we're trying to approach and above what we're trying to approach. So if we try 2.1 squared, we get 4.4. If we do 2. Let me go a couple of steps ahead. 2.01. So this is much closer to 2 now, squared. Now we're getting much closer to 4. So the closer we get to 2, the closer it seems like we're getting to 4. So once again, that's a numeric way of saying that the limit as x approaches 2 from either direction of g of x, even though right at 2 the function is equal to 1 because it's discontinuous, the limit as we're approaching 2, we're getting closer and closer and closer to 4.
Yeah. Okay, cool. To understand what limits are, let's take a look at an example. We start with the function f of x equals x plus 2, where, right, we have some linear function, x plus 2, where we have y-intercept at 2. Okay? Got you with that 1-to-1 slope. Perfect. The limit of the function at x equals 3 is the value the function approaches as we get closer and closer to x equals 3. So as x equals 3 here, the value that we get to would be equal to 5 as we get closer and closer to x equals 3. Graphically, this is the y value we approach when we look at the graph of f and get closer and closer to the point to the end of the graph where x is equal to 3. For example, if we start at the point 1, 3 here and move on the graph until we get really close to x equals 3 here, right? Then our y value, the function's value, gets really close to the value of 5, right? Perfect. Similarly, if we start at 5, 7, we move left until we get close to the value of 3, the y value then converges again on the value of 5. For these reasons, we state that the limit of the function at x equals 3 is 5. Okay, got you. You might be asking yourself, what's the difference between the limit of f at x equals 3 and the value of f at x equals 3, i.e. f of 3? So yes, the limit of f of x equals x plus 2 at x equals 3 is equal to f of 3, but this isn't always the case. To understand this, let's look at the function g. This function is the same as f, or as the function f, in every way except that it's undefined at x equals 3, right? We have this gap here. Just like in the function f, the limit of g at x equals 3 is 5, right? We've had the same answer. That's because we can still get very, very close to x equals 3, and the function value will give us very, very close values to 5. So the limit at g of g at x equals 3 is equal to 5, but the value of g at x equals 3 is undefined. They are not the same. So the limits can equal the values, but not always the case, because maybe you don't have the definition of that function at that value. That's the beauty of limits. They don't depend on the actual value of the function at the limit. They describe how the function behaves when it gets close to the limit. Okay. So limits describe the behavior of a function as it approaches a certain value, x value. So describe the behavior of a function as it approaches a certain x value. So problem 1, here's the graph of h, where we have some curve here with an undefined point at x3, y2. Okay. What is a reasonable estimate for the limit of the function h at x equals 3? Well, as we approach 3 from both sides of this graph, we converge on a y value of 2. The limit would be 2, even though it is undefined at this point. H of 3 is undefined, but the limit of h of 3 is going to be 2. Got you. So I will say okay. We also have a special notation to talk about limits. This is how we would write the limit f as x approaches 3, or the limit of blank, the function f, the limit of the function f as it approaches 3. Okay, so I'm going to take this. We'll paste this right into here. So limit notation, like so. The symbol lim means we're taking a limit of something, right? The expression to the right of the limit is the expression we're taking the limit of. In this case, that's our function f. And the expression x arrow 3 that comes below the limit, the lim, means that we take the limit of f as our value as values of x approach 3. Problem number 2. This is the graph of f. Right? What is the estimate for the limit of the graph f as x approaches 6? So as x approaches 6, we have a limit of -3, and we're undefined at 6 though. How's it going, Priya? And also busy learning a lot of stuff trying to get certain certificates. Nice. Welcome back. Appreciate you for being here. Let's get the TTS back on. All right. Which expression represents the limit of x squared as x approaches 5? So the expression of represents the limit of x squared as x approaches 5. So limit x squared, x approaches 5. Check. In limits, we want to get infinitely close. What do you mean if we want to say infinitely close? Let's take a look at the values. F of x equals x plus 2 as the x values get very, very close to 3. Remember, since we're dealing with limits, we don't care about f of 3 itself. So on f of x, given some values very, very close to as we approach 3, we get values close to 5. We can now see how when x values are smaller than 3 but become closer and closer to it, the values of f become closer and closer to the value of 5. But when we go over the 5. We can also see how when the x values are larger than 3 but become closer and closer to it, the values of f become closer and closer to 5. Notice that the closest we got to 5 was with f of 2.999 equals 4999, and f of 3001 equals 5.001, which are a thousandth of a unit away from 5. We can get closer than that if we want. For example, suppose we want to be like this 10 thousandths of a unit, or 100 thousandths of a unit away, whatever, from 5. Then we would pick a x equals 3.00001 and then
The
take
host
the
says,
function
what
of that.
certs are you going for?
This is endless. We can always get closer to 5, but this is exactly the infinitely close is all about. Since being infinitely close isn't possible in reality, what we mean by limit of f of x equals to 5 as x approaches 3 is that no matter how close we want to get to 5, there's an x value very, very close to 3 that will get us there. If you find this hard to grasp, maybe this will help. How do we know that there are infinite different integers? It's not like we've counted them all and we got to them infinitely. We know that they're infinite because for any integer, there's another integer that's even larger than that. There's always another one and another one and another one. In limits, we don't want to get infinitely big, we get but infinitely close. When we say that limit f of x equals 5 as x approaches 3, we mean that we can always get closer and closer to 5. So in this, problem 4, what is a reasonable estimate for the limit of g of x as x approaches -7? So as x approaches -7 here, right, we're passing over a value. We get 3.6, so let's try to visualize. So we're getting bigger, right? And then our x values are starting to shrink. And then they get bigger. This is a trickier one. What is a reasonable limit for g of x as x approaches -7? Well, obviously it never touches 6, but then it kind of curves back up. So we'll try it. Okay. Another example, limit x squared as x approaches 2. Let's analyze the limit of x squared as x approaches 2, which is the limit of the expression x squared when x approaches 2. We can see how when we approach, so in this one, as x approaches 2, right, we're converging on a limit of 4. We can see how when we approach the point where x equals 2 on the graph, the y values are getting closer and closer to 4. We can also look at the table of values. X squared, closer and closer to 4, yeah. Then this goes over. We can also see how we can get as close as we want to 4. Suppose we want to be less than 0.001 units from 4. Which x value close to x equals 2 can we choose? So let's try this value here. Where we square it, we get to this. That's more than this unit away from 4. All right, let's try this. All right, here. That's close enough, but by trying x values that are closer and closer to x equals 2, we can get even closer and closer to 4. In conclusion, the limit of x squared as x approaches 2 is equal to 4. A limit must be the same from both sides. Coming back to f of x equals x plus 2 and the limit of f of x as x approaches 3, we can see how 5 is approached when the x value increases towards 3. This is called approaching from the left, and whether they decrease towards 3, this is called approaching from the right. Now let's take an example of the function of h. The y values as we approach x values, the y value we approach as the x values approach x equals 3 depends on whether we do this from the left or the right. When we approach x equals 3 from the left, the function approaches x equals to 4. When we approach x equals 3 from the right, the function approaches x equals 6. When a limit doesn't approach the same value from both sides, we say that that limit does not exist. This is the function. Okay. So we'll say limit. We'll say when a limit doesn't approach the same value from both sides, the limit does not exist. Okay. So problem 5. Which of the limits exist? Choose all that apply. So limit of g of x as x goes to 3. Does that limit exist? So as we converge on 3 from the left, we get a limit of 3. And as we converge on 3 from the right, we get a limit of 6. So that does not exist. Limit as x approaches 5. This does exist. As x approaches 6, this does exist. And as x approaches 7, this does exist as well. First day learning calculus. All right, cool. So limits describe the behavior of a function as it approaches a certain value. You can approach a limit from the left and from the right. When a limit doesn't approach the same value from both sides, from both the left and right sides, the limit does not exist. Okay. I'm going to take this guy here. Like so. Control V. Keep doing that. There we go. There we go. Limit notation. Cool. That looks good. All right. If you guys are enjoying the calculus so far, leave a like. We just cleared up through Unit 1, Lesson 1 on limits intro. We're almost done here with this one. Okay. Describe the behavior of a function as it approaches a certain value. You can approach a limit from the left and from the right. When a limit doesn't approach the same value from both the left and right sides, the limit does not exist. Limit notation is also described as this. So I'm going to take this example here. Copy image. Let's go here and paste this one here. Nice. Okay, hold on. So, okay, let's see here. All right, ready for some practice? Show us what you can do with 4 practice questions. All right, you
Eduardo
guys.
says, this was totally unexpected. Why are you learning calculus?
Why not? I just want to keep learning and just learn as much as I can. And you know, I've been asked this question.
Think you need a dev team and a big budget to launch your
hold on.
Microsoft as a service idea? Wrong.
So I've been asked this question quite a bit, and it kind of actually is proving my point home. A lot of you guys are coming in here saying, "Oh, why are you doing calculus? You don't need to do calculus." Blah 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 blah. So it sounds like a lot of you guys, A, just either aren't good at it, or B, just don't care about it. So I'm going to be the guy that does care about it and the guy that does have good skills in calculus and programming in combination. And so when problems do arise, whether it be, you know, in regarding, you know, needing for some higher level math, I'll be the one to step up. All right, let's get into this. Let's keep going here. This is pretty easy so far, pretty fun. The function g is defined for all real numbers except for x equals to 5, right? We're undefined at this value. What is a reasonable estimate for the limit of g of x as x approaches 5? It's -2. The function h is defined over the real numbers. The table gives us a few values of h. So as we approach 6 as we approach...
Hariri says I don't know yet. PRBAI minus 900 to start course. I'm busy with a lot of things and I'm done.
So as we this reason as x approaches -6. The function is defined for all real numbers.
Tim says Mike, the music is blasting. I can't hear you, bro.
Oh, sorry.
Hariri says that's the way men start from scratch.
My fault. Sorry. Thanks, Tim.
Eduardo says, new question. Don't all scientists take calculus in math courses?
Yeah, I took calculus my freshman year of college, so it's a long time ago. So I'm wanting to go over it again here. Maybe we'll be able to move through it a little bit quicker this time around. Go through it again here and use Python though and programming to solve these calculus problems rather than writing out by hand or whatever. So I'm going to use Python to do it. Okay, so as x approaches -5 here, we do have two different limits that we're converging on from the left and right, so this does not exist.
Tim says Mike hasn't touched a math problem in 12 years.
Yeah, for real. The function h is defined for all real numbers. What is the estimate for the limit as we approach 0? It's undefined at 2, but the limit will equal to 2 there. Hey! Dun, 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 dun. Feels good.
Eduardo says, oh, kind of a numerical methods course.
All right. Sweet. This course makes it pretty fun to get through stuff. Exercise complete. Nice. Let me move this up so you guys can see. All right, next lesson here. Okay, so that was limits intro. Lesson is limit values from graphs. So I'm going to put, let's go back here. Call this, we'll make a heading called lesson, or unit 1, right? Calculus 1.
Tim says when's the exam?
Khan Academy, Calculus 1, Khan Academy, Calculus 1, Unit 1, Lesson 1. Unit 1. Okay, Unit 1. Okay, and we'll go here, we'll do Lesson 1, Limits, Intro. Okay, perfect. So then that'll be lesson 1. This is all under unit 1. So then this will be lesson 2. Okay, so I'm going to quickly take my limits definitions here. I'm going to throw them into the almighty orb and see what it says about them. You're giving a good start in explaining limits in calculus. Here's a cleaned up and slightly more structured version to improve clarity and flow. A limit describes the behavior of a function as the input, x, approaches a specific value, even if the function doesn't actually reach that value. That's a good, I like that. That's a better, cleaner definition. One-sided limits. You can approach a point from the left and from the right. If the left and limits are the same, then the overall limit exists at that point. Right, you can approach a limit from the left.
I forgot that the US educational system is more advanced than mine. I had to learn calculus in uni.
From the left and from the right.
Prism says hello, mate.
How's it going? Welcome in, Prism. All right. When a limit doesn't approach the same value from both the left and right sides, the limit does not exist. The limit of fx as it approaches a equals L. Okay, that was pretty easy so far. Moving up.
So we have the graph
And we want to figure out 3 different
Eduardo
limits. And like
says,
always,
in
pause
high
this video and
school,
see if you
I
can
only got
figure it
to
out
trig.
on your own before we do it together. All right, now first let's think about what's the limit of f of x as x approaches 6. So
The limit of f of x as x approaches 6 would be 1.
as x, this color you can see, as x approaches 6 from both sides, well, as we approach 6 from the left-hand side, from values less than 6, it looks like our f of x which is once again approaching 1. And in order for this limit to, and so here, let me do it in darker color. Now let's do this next one. The limit of f of x.
The limit of f of x as x goes to 4 would converge on an undefined point of 3, but it still would be 3.
But the limit as
Now, on the limit of f of x goes to 2, as x goes to 2, we have 2 different limits that we're imposing upon y values for, even though that the value of 5 is undefined, and we're defined for all real numbers except for 4, the limit would be undefined.
closer and closer to 1, closer to 5. And since we are approaching 2 different values from the left-hand side and the right-hand side, as x approaches 2 from the left-hand side and the right-hand side, we would say that this limit does not exist, which is interesting. In this first case, the function is defined.
Hey, Vance,
at
how's it
6,
going, dude?
and
Welcome
the
back in,
limit
my friend.
is equal to the value of the function at x equals 6. Here, the function was not defined at x equals 4, but the limit does exist. Here, the function is defined at x equals 2, but the limit does not exist as we approach x equals 2. Let's do another function, just to get more cases of looking at graphical limits.
Okay, the limit of g of x, this function g of x as x approaches 5, would converge upon some point that is about less than 0.5.
So here we have the graph of y is equal to g of x. And once again, pause this video and have a go at it. See if you can figure out these limits graphically.
The limit of g of x as x approaches 7 would converge upon a single point of 2. And then the limit of g of x as x approaches 1 would be, well, we're coming in and converging on 1. Oh, interesting. So we have an undefined value at 1, meaning we have an asymptote here at 1, if I remember correctly. So then, interesting. So the limit of g of x as x approaches to 1 converges on 2 separate values, right? So this one might be undefined as well.
So first, looks like we are approaching this value. So let me see if I can. So I'll say this limit definitely exists.
Less than 0.5, 0.4, yeah.
Roughly around there. Well, 0.9. It's like the function is defined there. At 999, it looks like we're just going unbounded towards infinity. And as we approach from the right-hand side, it looks like the same thing is happening. We're going unbounded to infinity. So formally, sometimes informally, people might say,
oh, because so we're parallel basically on either side representing, but the values aren't this. No, the values are the same. So this one would be
approaching infinity or something like that. But if we want to be formal about what a limit means in this context, because it is unbounded, we would say that it does not exist.
Oh, it does not exist. Okay, right.
Exist.
Okay. Unbounded limits. Okay, so let's do here. Lesson 2 is on estimating limits from graphs, right? Okay, so you have an unbounded limit. Okay, which we're going to talk about. Are you looking for grad programs? I want to recruit you. I don't know. What do you guys think about grad programs? How many of you guys are in computer science grad programs?
So right over here, we have the graph of y is equal to 1 over x squared. And my question to you is, what is the limit of 1 over x squared as x approaches 0. Pause this video.
So as x approaches 0, we're unbounded, right? We have an asymptote at x equals 0, so it's
We'll see if you can
undefined.
figure that out. Well, when you try to figure it out, you immediately see something interesting happening at x equals 0. The closer we get to 0 from the left, you take 1 over x squared, it just gets larger and larger and larger. It doesn't approach some finite value. It's unbounded, has no bound. And the same thing is happening as we approach from the right. As we get values closer and closer to 0 from the right, we get larger and larger values for 1 over x squared without bound. So a terminology that folks will sometimes use where they're both going in the same direction, but it's unbounded, is they'll say this limit is unbounded. In some context, you might hear teachers say that this limit does not exist, and it definitely does not exist if you're thinking about approaching a finite value. In future videos,
An unbounded limit occurs when the value of a function increases or decreases without bound, grows infinitely large or small as the input approaches a certain value. So occurs, an unbounded limit occurs when the values of a function increase or decrease without bound, i.e. grow infinitely large or small as the input approaches a certain value.
we'll start to introduce ideas of infinity and notations around limits and infinity, where we can get a little bit more specific about what type of limit this is. But with that out of the way, let's look at another scenario. This right over here, you might recognize as the graph of y is equal to 1 over x. So I'm going to ask you the same question. Pause this video and think about what's the limit of 1 over x as x approaches 0. Pause this video and figure it out.
Now, these are converging in opposite directions, though. So, although it might be unbounded, it might not follow the same principles.
All right, so here when we approach from the left, we get more and more and more negative values, while when we approach from the right, we're getting more and more positive values. So in this situation where we're not getting unbounded in the same direction, the previous example, we were being unbounded in the positive direction, but here from the left, we're getting unbounded in the negative direction, while from the right, we're getting unbounded in the positive direction. And so when you're thinking about the limit as you approach a point, if it's not even approaching the same value or even the same direction, you would just clearly say that this limit does not exist. Does not exist. So this is a situation where you would not even say that this is an unbounded limit or that the limit is unbounded, because you're going in two different directions when you approach from the right and when you approach from the left. You would just clearly say does not exist.
Okay. When a limit is unbounded, the limit, does not exist. Okay. All right. There's an important difference between the values the value a function is approaching. There's an important difference between the value a function is approaching, what we call the limit, and the value of the function itself. Graphs are a great tool for understanding the difference. In the example above, we see that the function value is undefined, right? There is a gap at this point at 2, when the limit value is approximately 0.25. Yep. Just remember that we are dealing with an approximation, not an exact value. Examples. The examples below highlight interesting cases of using graphs to approximate limits. In some of the examples, the limit value and the function value are equal, and in other examples they are not. Sometimes the limit value equals the function value. What is a reasonable estimate for the limit g of x as x approaches 1 for this graph here? So this function g of x as x approaches 1, as we're converging on 1, we're converging on a value of about negative 1.2 or something. 1.4. Nice. But sometimes the limit value does not always equal the function value, right? You have a defined point which is at a different point than the graph here. Whatever you're dealing with a piecewise function, it's possible to get a graph like the one below. What is the possible estimate for the limit of g of x as x approaches 1? So on this function g of x here, as we approach 1, we're converging on a point that is a little bit greater than 4 for the function, even though that is undefined at that point and has definition elsewhere. So 4.2, check. It's possible for a function value to be different from the limit value. And just because a function is undefined for some x value doesn't mean that there's no limit. Holes in the graph happen with rational functions which become undefined when their denominators are 0. Here's a classic example. Holes in a graph happen with rational function which become undefined. Okay, got you. So this is a graph of y equals x divided by the sine of x. Notice that there's a hole at x equals 0 because the function is undefined there. Where if you have sine, you can't take the sine of 1 is 0. So it's undefined there. You can't divide by 0. In this example, the limit appears to be 1 as we converge on this from both directions, right? Because that's what the y value seems to be approaching as our x values get closer and closer to 0. It doesn't matter what the function is undefined at 0. The limit still exists at that value. Here's another problem for you to try. What's a reasonable estimate for the limit of f of x as x approaches, oh, it's cut off here. -4. Be a little bit greater than 3. The function value at x equals -4 is irrelevant to finding the limit. All that matters is figuring out which the y values are approaching as we get closer and closer to the x equals -4. Awesome, Sophonias. I'll be right there with you hopefully soon. We're going to get through this. I'm wanting to, take my baby steps in order. I know I could jump the gun and just skip, maybe to Calc 2 and into linear algebra and stuff, but it's honestly been over 5 years since I've done calculus and like more advanced algebra stuff. So I wanted to, take this time to refresh. I'm in no rush to learn the concepts. So I wanted to really kind of get into this and yeah. All right. On the flip side, when the function is defined for some x value, that doesn't mean that the limit necessarily exists. Uh-oh, we got a spammer in here. Get out of here. Got him. On the flip side, when the function is defined for some x value, that doesn't mean the limit exists necessarily. Just like in an earlier example, the graph shows the sort of thing that can happen when you're working with the piecewise functions. Notice how you're not approaching with the same y value as you approach both sides, x equals 3. So from the left, we're converging on 4, and from the right, we're converging on -3. So this limit does not exist. Oh, whoops. Graphing calculators are pretty slick these days. Graphing calculators like Desmos can give you a feel for what's happening to the y values as you get closer and closer to a certain x value. Try using a graphing calculator to estimate these limits. Okay. I guess we'll go to Desmos. And we're going to try to evaluate the x equal divided by the sine of x. So this is this function here. And as we approach 0, we converge on 1, right? And then for x minus 3 divided by x squared, less than 9. As we converge on to 3, right, our limit looks like it's going to be about 1.664, something like that. In both cases, the function isn't defined at the x value we're approaching, but the limits still exist and we can estimate it. So summary questions. Is it always true that the limit of f of x equals to f of a as x approaches to a? Is it always true that the limit? No. Right? We know that. That's not true. It's not always a is the answer is equal to the limit. No. Which statement better describes how graphs help us reason about limits? A graph can help us approximate a limit by allowing us to estimate the finite y values we're approaching as we get closer and closer to some x values. A graph is a great tool for finding exact value of the limit. Here we go. I think this is it. Yeah. Nice. Up next exercise. Yeah, take your time for sure. Everything builds on Calc 1 perfectly, so that base knowledge is real important. Yeah, exactly why I wanted to kind of go through Calc 1 again. And the more math you know, the better. There's never been a thing where too much information was going to hurt a person. Yeah. I took calculus while trying a CS degree. I'm convinced that is to give you the tools used for problem solving. But why are you wasting your time on this? Am I really wasting my time? Just hanging out here after my job. Maybe to you, it's considered that, but to anyone, how they spend their time is valuable to however they spend their time. An undergraduate course or unrelated to math, CS or math, like soil, may help a trader predict to purchase fertilizer. Nightmare, I'd suggest maybe learning more about the channel before coming in soliciting like advice and stuff. All right. Let's keep on going. Next. Let's go. The function f is defined for all real numbers. What is a reasonable estimate for the limit of f of x as x approaches -5? Well, it's undefined, or its limit doesn't exist. Right. Nice. The function h is defined for all real numbers. What is a reasonable estimate for the limit of h of x as x approaches -2? Well, it looks like we're converging on a little bit value of greater than -4, so 3.8. Nice. Hey, Walkthrough Killer, how's it going? Yeah, we're starting up a calculus course here. I wanted to dive deeper into my personal math journey and knowledge and solidification. I've taken Calculus 1 back in my freshman year of college, but it's been a long time, and I want to learn more about it and incorporate it into programming. More specifically, I'm doing calculus because I am interested in making some like financial algorithms using like trading algorithms and stuff. So I want to really have a solid basis of calculus to move forward and then go into linear programming and things like that. The more we know, the better. Okay. The function f is defined for all real numbers. What is a reasonable estimate for the limit of f of x as x approaches -6? It's going to be down here at this guy at about -5.7. Woo! Hold on. The function h is defined for all real numbers except 0. Yeah, awesome. Big O uses limits, so it's good to know how they work. Yeah, exactly. So far, so good. I'm definitely understanding these a lot better than I did when I was 19. Let me tell you. When 19, I was focused on what girls in my class were good looking and what I was doing that Friday night. Now that I'm just focusing on the math part, it's a lot easier. You guys notice that? That's kind of easier to learn stuff out of college because honestly, I am not as distracted with so much stuff now that I have no life here. The function h is defined for all real numbers except for x equals to 0. What is a reasonable estimate for the limit? Well, if it's undefined for x equals 0, but we're converging on a asymptote, right? So this one's going to be doesn't exist. Woo! Hey! Come on, boys! Round it up. If you guys are here, learn on us alongside me, and you're wanting to, you always had a goal on your own to, learn calculus, then this is your chance, guys, to do it with a friend and do it with someone. Make it a little bit more fun rather than just grinding by yourself. If you guys are here, leave a thumbs up, leave a sub. I appreciate you guys joining me. You guys are awesome. Thanks so much for joining me tonight. Okay. So, limits from graphs, unbounded limit. An unbounded limit occurs when the value of a function... Oh, my headphones are dying. I gotta charge them. Hold up, guys. Pardon me. Gotta charge for about 5 minutes. An unbounded limit occurs when the value of a function increases or decreases without bound. It grows infinitely large or small. Does not exist. Nice. Up next is a video here. So should we finish lesson 2 tonight? And then maybe we can, if you guys, should I do it? Should I play a game of League tonight? As a celebratory? I told you guys. Oh my gosh. I'm already fluent in Python, my friend. I've already been coding in Python every single day for the past year for a minimum of 2 hours. Written multiple projects in Python, and so we're just using math to further solidify our knowledge in Python by using Python and certain libraries to perform like derivative calculations and things like that. So, yeah. There's always going to be people out there, you guys, that'll tell you, you're doing the wrong thing, or you're wasting your time, or they're going to shoot you down. But at the end of the day, you sitting in your room working on whatever you want to work on really is no one else's business but your own. And just because I'm streaming it, there's no difference. So, be solid in yourselves and have confidence in what you're learning and your goals, because, people don't value education like we value on this channel. We show firsthand just how far, learning and teaching yourself can go. We've already crossed 2,300 subscribers from nothing just by teaching ourselves basic educational stuff from scratch here. Not basic, but more advanced computer science. Freshman Mike looking for hot girls. Up on GTA or Minecraft, Locker League. I don't have those. I'm only on a Mac, so we're limited on the games we can play via while streaming too. So I can't run too heavy of stuff. So I was thinking we play like a game of League or something afterwards tonight. I haven't played a game of League of Legends in like 2 years, you guys. But I need to know, so because we need to download it in the background. Start at 4th grade if you need to. That would be a little bit boring, starting at like basic functions. Just algebra 1. That'd be brutal. I wouldn't stream that live. Okay. Cryptography and discrete math. Yeah, so I want to get into more about that stuff too on the channel. So like the whole point of this channel is just to, continue learning and just as much as I can. So I want to get into, discrete math, and then eventually into like cryptography and those types of like decoding and stuff like that, I guess. I left calculus in first and second semester in uni 1998. I'm still reviewing math to this day. Awesome, dude. We got some experience in here, Eduardo. Appreciate you for being here. A good resource that I have is read numerical Python. Yeah, we'll have to. That's a good one. You want to drop that one in the Discord duo? Okay, let's keep chugging here. We're almost. It'll go by quick here, you guys.
So if we were to ask ourselves, what is the value of our function approaching as we approach x equals 2 from values less than x equals 2? So as you imagine, as we approach x equals 2, so x equals 1, x equals 1.5, x equals 1.9, x equals 1.999, x equals 1.999,
Converging close to 1.
what is f of x approaching?
But we're
And we see
in
that
two
f of
different
x
places.
seems to be
A
approaching
5.
this value. Seems to be approaching this value right up here. It seems to be
But our
approaching.
limit isn't. It doesn't
The way we
exist.
would denote that is the limit of f of x as x approaches 2, and we're going to specify the direction. As x approaches 2 from the negative direction, we put the negative as a superscript after the 2 to denote the direction that we're approaching. This is not we're approaching 2 from the negative direction. We're approaching 2 from values less than 2. We're getting closer and closer to 2, but from below, 1.9, 1.99, 1.99999. As x gets closer and closer to from those values, what is f of x approaching? And we see that it is approaching 5. It is approaching 5. But what if we were asked a different question, or I guess the natural other question?
The positive side.
What is the limit of f of x?
So rather than defining, so what he's trying to get into here is rather than defining limits totality, like in terms of the overarching function, you can define them from a specific direction.
From values greater than 2. So this is a little superscript positive right over here. So now we're going to approach x equals 2, but we're going to approach it from this direction. X equals 3, x equals 2.5, x equals 2.1, x equals 2.01, x equals 2.0001. We're going to get closer and closer to 2, but we're coming from values that are larger than 2. So here, when x equals 3, f of x is here. When x equals 2.5, f of x is here. When x equals 2.01, f of x looks like it's right over here. So in this situation, we're getting closer and closer. We're getting closer and closer to f of x equaling 1. It never does quite equal that. It actually then just has a jump discontinuity, but it seems to be approaching. This seems to be the limiting value when we approach x from values greater than, or when we approach 2 from values greater than 2. So this right over here is equal to 1.
Yeah.
And so this is, and so when we think about limits in general, the only way that a limit at 2 will actually exist is if both of these limits, both of these one-sided limits are actually the same thing. In this situation, they aren't. As we approach 2 from values below 2, the function seems to be approaching 5. And as we approach 2 from values above 2, the function seems to be approaching 1. So in this case, the limit, let me write this down, the limit of f of x as x approaches 2 from the negative direction does not equal the limit of f of x as x approaches 2 from the positive direction. And
limits can be defined on a local scope relative to the direction of the scope. Approach, so we'll say like approaching a limit from the left negative and approaching a limit from the right positive. Right? If the limits defined from each direction are not the same, the limit does not exist. Doesn't exist, right? Something like that. So let's take this, throw it into the orb, and see what it has to say about that definition. You're on the right track. Here's a refined version. A one-sided limit describes the behavior of a function as x approaches a specific value from only one side, either left or the right. Left-handed limits approaching from the left, where it has a notation of this. So if I, okay, I like that better than mine. Approaching, so left hand limit. Right. And then if I copy this, what does that do? That just gives a superscript of a negative, right? If I shift control V and look at this, no, it doesn't auto format it. No. Find with a negative superscript on the limit path, and then the right hand limit defined with a positive superscript on the limit path. Notation. If limit's defined, does not exist. Okay.
Since this is the case that they're not equal, the limit does not exist. The limit as x approaches 2 in general of f of x, or the limit of f of x of x.
Hey Ray, what's going on?
The limit
Welcome
of f
back
of x
in,
as
dude.
x approaches 2 does not exist. Does not exist. In order for it to have existed, these two things would have had to been equal to each other. For example, if someone were to say, what is the limit of f of x as x approaches 4? As x approaches 4, well, then we can think about the two one-sided limits, the one-sided limit from below and the one-sided limit from above. So we could say, well, let's see, the limit of f of x as x approaches 4 from below. So let me draw that. So we care about x equals 4. As x equals 4 from below, so when x equals 3, we're here, where f of 3 is negative 2. F of 3.5 seems to be right over here. F of 3.9 seems to be right over here. F of 3.999. We're getting closer and closer to our function equaling negative 5. So this, the limit as we approach 4 from below, this one's f of 4 equal to the limit from the limit of f of x. Now this is our new f of x depicted here. As x approaches 8, and let's approach 8 from
the left. So as x approaches 8 from the negative direction, our limit will be positive 4.
As x approaches 8 from values less than 8. So what here? So it looks like our value of f of x is getting closer and closer and closer to 3.
Oh, to positive 8. Sorry, not negative 8. So positive 8 from the negative direction. So we're going to be converging on 3 here. But you have, a different function, which limit of 1 here when converging from the right. So this. So
it looks like the limit of f of x is x equal, as we have not. The function f is does not exist.
Yeah.
Let's do one more example. And here they're actually asking us a question. The function f is graphed below. What appears to be the value of the one-sided limit? The limit of f of x, this is f of x, as x approaches 2 from the negative direction, as x approaches negative 2 from the negative direction. So this is the negative 2 from the negative direction.
Function f is graphed below. What appears to be the value from the one-sided limit of f of x as x approaches negative 2 from the negative direction. So as we approach negative 2 from the negative direction with this one-sided limit, we're converging on a limit of positive 4. And as we approach on negative 2 from the positive direction, we're also converging on positive 4. So that limit does exist at 4.
Equal of x is x tells the limit. We would get a similar when x is 1 to be it and the right limit, and this is from 2. From both directions, since from both.
That one was pretty easy. One-sided limits.
So over here we have the graph.
It's only 2 minutes.
The graph of y is equal to g of x. And what I want to do is I want to figure out the limit of g of x as x approaches positive 6 from values that are less.
So as x approaches positive 6 from the negative direction, we're converging on a value of negative 3 here. We're undefined. Ah, so interesting. So this one is going to not exist either. Well, maybe actually, this one's interesting because from the negative direction, you have a limit that doesn't exist. But from the positive direction, you do have a limit that exists.
Less than positive 6, or you could
I
say
want to
from
see what
the
this one. What do you
left,
guys
from
think
the,
of this
you
one?
could say the
I'm gonna
negative
pause this one.
direction.
Let's ask chat. What do you guys think? What do you guys think about this one? So you have a piecewise function here where you have coming from the negative direction, you go to infinity upon converging on your asymptote at 6. But from the positive direction, you are just undefined at 6. What do you guys think for this one before I continue? Let's ask chat here. I struggle with motivation sometimes, especially at your lowest when you're almost everybody is only. I struggle with motivation sometimes, especially at your lowest when almost everybody you know is unknowingly kicking your dying passion in its yeah. Does not exist, Eduardo says.
So what is this going to be equal to? And if you have a sense of it, pause the video and give a go at it. Well, to think about this, let's just...
So Eduardo says doesn't exist. So if you're coming in from the left side and you're going up to negative infinity, but you're still undefined coming in from the right side, you're undefined at both places.
Let's just take different x values that approach 6 from the left and look at what the values of the function are. So g of 2 looks like it's a little bit more than 1. G of 3, it's a little bit more than that. G of 4 looks like it's a little under 2. G of 5, it looks like it's around 3. G of 5.5 looks like it's around 5. G of, let's say, 5.75. So it looks like it's like 9. And so as x gets closer and closer to 6 from the left, it looks like the value of our function just becomes unbounded. It's just getting infinitely large. And so in some contexts, you might see someone write that. Maybe this is equal to infinity. But infinity isn't we're not talking about a specific number. And if we're talking technically about limits, the way that we've looked at it, you'll sometimes see this in some classes, but in this context, especially on the exercises on Khan Academy, we'll say that this does not exist.
They question the journey, show them the bag.
This thing
what
right
bag?
over here is unbounded. And this is interesting because
What
the left-handed
bag?
limit here doesn't exist, but the right-handed limit does. If I were to say the limit of
Where's
g
the
of
bag,
x
Tim?
as
I would like
x
to know where this
approaches
bag
6
is.
from the right-hand side. Well, let's see. We have g of 8 is there, g of 7 is there, g of 6.5 looks like it's a little less than negative 3, g of 6.01, little even closer to negative 3.
Got you. So even though it doesn't exist because the overarching function doesn't have the two limits from both directions equal to one another. This one doesn't exist. This one does exist. It converges on negative 3. D does not exist, or infinity and negative 3 are not the same. So that's why the overarching function is right. I got you. So you have to set these equal to one another in order for that to exist, like we talked about earlier.
0.000001 is very close to negative 3. So it looks like this limit right over here, at least looking at it graphically, it looks like when we approach, the function is approaching negative.
Oh, he doesn't actually go over the overarching, but interesting. Okay. All right, 4 questions here. The function g is graphed. Y equals g of x. What appears to be the value of the limit of g of x as x approaches 4 from the positive direction? So as x approaches 4 from the positive direction, the limit would be 5. Whoa! What is the value of the limit of g of x as x approaches 1 from the negative direction? So as x approaches 1 from the negative direction, the limit's going to be 1 from the negative direction. Woo! What appears to be the value of limit of h of x as x approaches negative 4 coming from the positive direction? So as we come from the positive direction, our function becomes unbound. What appears to be the value of the limit of h of x as x approaches negative 2 from the negative direction? So as x approaches negative 2 coming from the negative direction, we do have a limit defined here on negative 6, but coming from the right, we have an unbound. So the overarching limit is undefined, but coming from the left here at negative 2, let me make sure that this is the right. Yeah, negative 2 from the left would be -6. Woo! Hey! Bop, 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 bop. All right. Sweet. Haha. Look at that. Both sides, if the limit from both sides exists and equals the same value, the function is also said to be continuous at that point. Okay, gotcha. All right, almost there, you guys.
So we have the graph of y is equal to g of x right over here. And I want to think about what is the limit as...
Question for you guys. How long do you think it took him to, like... I honestly, I really would have liked to seen Khan Academies back in the day, back in like 2000 and like whatever he did, 2003 or whatever, 8, he made these. I would have really liked to have seen his like workflow for how he like pounded these out, because I think I remember watching like a small little documentary or something on him, and if you and he said that he just got a textbook and would read the textbook and then make videos on it. And so it's really crazy that he was able to read the textbook and then make such simple videos that just have such lasting impact. He's honestly one of like the greatest probably educators of our generation, like in terms of like if you really think about it.
X approaches 5 of g of x. Well, we've done this multiple times. Let's think about...
So the limit of g of x approaches 5. Well, it's going to be -6 because we're coming from both directions and we're converging on that same
x
point.
Approaches 5 from the left. G of x is approaching -6. As x approaches 5 from the right, g of x looks like it's approaching -6. So a reasonable estimate based on looking at this graph is that as x approaches 5, g of x is approaching -6.
I think it was just like a 60 minutes, Muna. It was like a 60 minutes or like one of those like just TV kind of segments things.
It's worth noting that that's not what g of 5 is. G of 5 is a different value. But the whole point of this video is to appreciate all that a limit does. A limit only describes the behavior of a function as...
I'm honestly surprised that he hasn't like won, honestly, that he didn't win like a Nobel Prize. Now that might be kind of crazy to think about, but like honestly, like think about it though, like the reach, the educational reach worldwide his videos for math has done for like creating the next generation of mathematicians or whatever, I bet you. It's probably pretty crazy.
Approaches a point. It doesn't tell us exactly what's happening at that point, what g of 5 is, and it doesn't tell us much about
Bill
the rest
Nye.
of the function,
Nah, he
about
was
the
just
rest
like,
of the graph.
he wasn't
For
much of a
example, I
scientist,
could
honestly. He
construct
just
many
was more of
different
a
functions for
celebrity
which
figure.
the limit as x approaches 5 is equal to -6, and they would look very different from g of x. For example, I could say the limit of f of x as x approaches 5 is equal to -6, and I can construct an f of x that does this, that looks very different than g of x. And in fact, if you're up for it, pause this video and see if you could do the same, if you have some graph paper, or even just sketch it.
So what does he want me to do?
Very different from g of x. For example, I could say the limit of f of x
So a different
as
function.
x approaches 5 is equal to -6, and I can construct an f of x that does this, that looks very different than g of x. And in fact, if you're up for it, pause this video and see if you could do the same, if you have some graph paper, or even just sketch it. Well, the key thing is that the behavior of the function as x approaches 5 from both sides, from the left and the right, it has to be approaching -6. So, for example, a function that
A
looks
linear
like
function?
this. So let me draw f of x.
With a negative
An
slope?
f of x that looks like this, and is even defined right over there, and then does something like this.
Or an absolute value or
work.
something?
As we approach from the left, we're approaching -6. As we approach from the right, we are approaching -6.
Yeah, you could do an
could
absolute
have a
value
function
function or just a linear
like
function. Or
This, let's say the limit, let's call it h of x, as x approaches 5 is equal to -6. You could have a function like this. Maybe it's defined up to there, then you have a circle there, and then it keeps going. Maybe it's not defined at all for any of these values, and then maybe down here it is defined for all x values greater than or equal to 4, and it just goes right through -6. So notice, all of these all of these functions as x approaches 5, they all have the limit defined and it's equal to -6, but these functions all look very, very, very different. Now, another thing to appreciate is for
See you, Andy. Thanks for coming in, bro.
Oftentimes,
Really appreciate you coming in, man, guy.
X approaches some type of an interesting value. So, for example, x approaches 5. 5 is interesting right over here because we have this point discontinuity. But you could take the limit on an infinite number of points for this function right over here. You could say the limit of g of x as x approaches, not x equals, as x approaches 1. What would that be? Pause the video and try to figure it out. Let's see.
So the limit of g of x at x approaches 1 would converge on this point down here at -5 point, like 2.
As x approaches 1 from the left hand is to g of 1. That is equal to g of 1 based on, that would be a reasonable, that would be equal to g of 1. That is equal to g of 1 based on that value there, here. 1 from the left hand side, it looks like we are approaching this value here. And as x approaches 1 from the right hand
Okay,
side,
so he's saying it would equal to just g of 1,
so
which
that
would be
equal to
another
g of 1.
representation
That
of...
is equal to g of 1 based on, that would be a reasonable, that's a reasonable conclusion to make looking at this graph. And if we were to estimate that, g of 1 looks like it's approximately
-5.1.
-5.1 or 5.2, -5.1. We could find the limit of g of x as x approaches pi. So pi is right around there. As x approaches pi from the left, we're approaching that value, which is actually pretty close to the one we just thought about. And as we approach from the right, we're approaching that value. And once again, in this case, this is going to be equal to g of pi. We don't have any interesting discontinuities there or anything like that. So there's two big takeaways here. You can construct many different functions that would have the same limit at a point. And for a given function, you can take the limit at many different points. In fact, an infinite number of different points. And it's important to point that out, no pun intended, because oftentimes we get used to seeing limits only at points where something strange seems to be happening.
Interesting. All right, 4 questions. Which graphs, consider graphs A, B, and C. Which graphs agree with this statement that the limit as x approaches -1 from the negative direction is equal to f of x of 2? So here we would say as we approach -1 from the negative direction, x of x equals 2. Well, this is undefined at that point in time. But that limit it would be this one and this one. C would not, because you converge on -1 coming from the left. All right, consider the graph of the function h. Which limit expressions agree with the graph? All right, so limit of h of x as x approaches -3, so the limit of it is 3. So as we approach -3, the limit is 3. No. So that is not true. How about the limit of h of x equals to 1 as x approaches 3 from the positive direction? So as x approaches 3 coming from the right, h of x is equal to 1. Right? That is true. The limit h of x does not exist for x equals as x approaches 3 from the negative direction. That is false. It does exist. It is -3. The limit does not exist overall for the function, however. So I think that's my answer. Woo! What do I work as? Hey, Stormy. Or Strami. I have a degree in human biology and a minor in chemistry. I'm 26 years old. I appreciate those who are joining in. Please subscribe if you're new here and consider liking. I stream every single day. Today is day 1 of us starting to learn and teach ourselves calculus again. From back when I learned it in freshman year of college, and more specifically using Python to learn calculus. Do you enjoy math? I lose focus on this immediately. Yeah, we've been doing an hour 45 minutes of studying so far into calculus here. So join along here if you're interested in learning math alongside me, having someone else learn it with you, could help if you're struggling. All right. Consider the graphs A, B, and C. Which graphs agree with the statement that the overall graph for g of x as, oh my gosh, that the limit for g of x is equal to 5 as x approaches 3. So as x approaches 3, we get a limit of 5 here, so that is true. As x approaches 3 here, we get a limit of 5, that is true. As x approaches 3, we get a limit of 5, that is also true. Boom. All right, consider the graph of the function h. Which limit expressions agree with this graph? So the limit h of x equals to 2 as x approaches negative 4. So as x approaches negative 4, from both directions, we converge on a limit of negative 2. That is false. We have a limit of negative 6 down here. As x approaches 0 from the positive direction, the limit is equal to 2. That is true. The limit of h of x is equal to 2 as x approaches 4 from the negative direction. So as we approach 4 coming from the negative direction, we also converge on a limit of 2. That's true. Woo! Hey! Calc Pro, come on. All right, we have one more video here, and then that's probably where we'll stop it for today on math.
So we have a function f of x graphed right over here, and then we have a bunch of statements about the limit of f of x as x approaches different values. And what I want to do is figure out which of these statements are true and which of these are false. So let's look at this first statement.
Okay, so the limit of f of x as x approaches 1 from the positive direction is equal to 0. So as x approaches 1 from the positive direction is equal to 0, that is going to be true.
Limit of f of x was this one closer and closer from the positive is not true. Is it 0? It looks like it is 1.
Oh, wait, sorry. I didn't see this over here. I thought that the function kept going here. I didn't see this over here. My bad. So yeah, as we approach on this over coming from the positive, I thought it kept going on the x here. So no, it goes here, it's not equal to 0, it's equal to 1. So that's false. The limit of f of x equals to 1 as x approaches 0 from the negative direction. So as x approaches 0 from the negative direction is the one that is going to be true.
Of x is 1 x as we approach the value of f of x. As we get even closer.
How about this one? F of
the limit is 1. So this is
so f of x 0 is equal to 1. They're both equal to each other. Yes, that is true.
Absolutely true. To 1. The limit closest is true.
That one's true.
Now the limit of f of x as x approaches 1 exists.
As x approaches 1 exists. That is false.
The limit is a little bit more than 1. It's 1. So it seems like we're getting f of x. He values different than 1. The function.
So the limit of f of x is equal to 1 as x approaches 1.5. So as x approaches 1.5, we're equal to 1. That is true.
So every time it is indeed the case 1.
Which it was. Perfect. All right. That was pretty simple. Honestly, that was not that hard at all. Pause. Hold on one second. I want to see if we can get a piece of notes here. One-sided limits, graphs. All right, cool. What's going on here? What is going on? finished. We finished Unit 1, Lessons 1 and 2. Oh, this isn't supposed to be there. What the heck? Okay, cool. So yeah, you guys can get access to these notes on my GitHub if you're wanting to follow along with what I'm doing here on stream. So we have a limits intro with lesson 1. Lesson 2 is estimating limits from the graph. And then, right, we finished lesson 2 here. Up next is lesson 3, which is estimating limits from tables. Nice. All right. How do you guys like it so far? Are you guys enjoying the course? I'm just taking Calc 1. I'm doing electrical and engineering as a degree, and I'll be learning software dev soon. How has your journey been so far? It's been a lot of fun. I really enjoy learning and doing this process. It's been I can say I can feel myself becoming easier and easier to pick up these topics and teach myself these concepts. At least for this introduction here on limits and remembering limits back from 2018 or 2019 when I took the course. It's coming up. It's coming back fairly quick here. So it doesn't seem too bad so far. I misspoke. The point missing from the previous statement is that the function must also be defined at that point and equal to the limit. Okay, gotcha. What do you guys think so far? Do you guys enjoy it? It's very well formatted here. This is a really nice. They've got it really, really organized for flowing you through the course. I really like the videos and the practice problems that they've given you baked in. It really helped to solidify this limit from both directions and the overarching limit as well. So I'm understanding really well these first two lessons here, lesson 1 and 3 of unit 1. So what happens if I go back to, let's just go to my course here. So unit 1, we need to do all of these. And so what are these?
Stromy says, the chemistry tutor also has some great videos on calculus.
Practice what you've learned with 6 questions on quiz 1. And then unit test, 31 questions at the end here. Okay. Oh boy. Oh boy. We have a unit test and everything. Oh no, what are we gonna do? All right, what do you guys want to do? Should we do leak code? Should we play a game, or should we code on the project? Or should we be done for the evening? You guys think we've done enough for today? It's only.
Ho says, I mostly learned calc from Professor Leonard on YT. He is great.
Yeah. Some people have mentioned him in here. Alrighty. I'm kind of nervous if we play League because I haven't played in a long time.
Eduardo says, black pen, red pen is also great. Ho says 1 lead code Q.
Ow, crap, that hurt really bad. The bad thing about standing desks is that the stupid little controller thing sticks out. I hit my knee on it all the time. There's also some like plastic over the buttons here that's like peeling up. The heck? I didn't notice that before. Oh well. I think it's just cheap. One lead code Q? You guys are killing me. Okay. Let's figure out what to do here. Is subsequence 392. A subsequence of a string is a new string that is formed from the original string by deleting some.
Jamie
Can be
says,
none
do the
of
daily
the
question,
characters.
bro, so easy.
Daily question? What's the daily question? Oh boy. You are given an integer array of numbers with a certain length and a 2D array of queries, where queries at some index is Li and Ri. For each query's index I, select a subset of indices within the range Li, Ri in numbers. Decrement the values by selecting these by 1. What? Okay. For each queries, select a subset of indices. A zero array is an array where all elements are equal to 0. So you have a bunch of queries, which are Li and Ri, which are what? Left index, right index in numbers. Select a subset of indices. So this is our original numbers. This is our query of 0 and 2. Select the subset of indices as 0 and 2 and decrement the values as those indices by 1. So 0 and 2 got decreased by 1.
Oh, not gonna lie, bro. I forgot the daily question changed. I meant yesterday's. Didn't get to see today's yet.
I was wondering, I was looking at this and I'm like, dang, Jamie! Jamie kicking it over here.
Jamie says, but I think you got this one too, haha.
So you go to 1 and 3, and you decrease those. So it becomes 4, 2, 1, 0. Then you go to 0 and decrease those. So a 0 array is an array where all elements are equal to 0. So I don't really get though, so it's saying that I have these left and right indices in these queries that I need to decrease the indices that are proportional Okay, so we say like for query in queries, right? This is going to give us left is equal to query index 0, and right is equal to query index of 1. We want to go into numbers at index of left, subtract equal by 1, numbers at index right, also subtract equal by 1. And so we're going to do a loop through every query and subtract the proportional index in that query by 1.
Stromy says if you do -1 it automatically does the rightmost number in the index.
Yeah. Yeah, so you could put a -1 here to do the rightmost number in the index, but it's only 0 and 1. We know that, so it's whatever. Okay, so then decrement all the values by the selected indices by 1. A 0 array is an array where all elements are equal to 0. Return true if it's possible to transform numbers array into
Ayosh says from where you are learning.
So the thing is now we just have to say, like, the thing is though, is we need to say, can we do this in a single loop over our queries, or do we have to check over these? We have to say like for value in numbers, if value is not equal to 0, then we're going to return false. Else we're going to return true at the end of this loop, meaning we found them all.
Stromy says in the example I guess 0 and 2 are the index value for nums.
Okay, so in nums2, 0, 0, 0, 0 decreases index 0 by 1 and index 0 by 1. That makes it 0.
Stromy says so if it was queries equals 1, 2, it would be false since nums 1 is 0 already and it'd make it -1.
I guess in the example, queries are 1 and 2.
Nugs
Hey,
says
Nugs.
hello.
Okay, so we're getting this is going false. So this is going nums index 0 and 0. So that's decreasing that by 2. So that's already going to 0. Now it's going to -2. But it's expecting to return true because this query did return it to zeros. Return true is possible to transform numbers right after processing all the queries. What? So this array becomes, after this one, this becomes 0, and then after this query, this becomes -2. Can you not subtract from a 0? By 1. Current loop looks to subtract the indexes number by 1. Not the entire range. Oh, you do the range of 0 to 2, you subtract by 1? Oh. A subset of indices within the range of left to right. Okay, so it wants us to subtract. Oh, okay, so it is a range of indices. Okay, my bad. I didn't get it. I didn't see that. Okay, so we have left and right here. We say for I in range left to right plus 1. Nums index I less than or equal to 1. So now let's go here to description. So we'll take this, use this test case. Let's run it. Oh! I'm getting outputs false. Expected should be true for here. So 0 to 2, so we're down by 1. Where's my chat at? Where did my chat go? Where did my chat go? Oh no. Where's my chat? Oh, here it is. Okay. For every query and query. So the thing is I've done work over this numbers range. We reduce it by 1. If the value is equal to 0, not equal to return false right away. Let's return true at the end of the loop. So why am I getting false? So if I run this, I fail the first test, which is this guy here. So between 0 and 2, I'm outputting false. So I'm sorry. So 0 and 3 excluded. So 0, 1, and 2 are going to be reduced. Let me take this into my... Okay, this is number 3355. Def is 0 array. Okay, and we're gonna have nums equals this and queries. Okay, so let's go to our test cases. Call is zero array given nums queries. False given true.
This way and says bro as query and queries there should be possible cases then the given query index is out of range, ultimately means invalid index. Nums hasn't extinct
Okay,
of
so
the
let's
index.
see here. So if we put in our debug here, step into, okay, so 0 and 1, queries is 0 and 2, left is 0, right is 0. So num 0, 0. So we're getting a negative 1 here. So it becomes 0 and 2 for query.
This way and says let's say num equals 2, and query is 100 to 102. That means invalid query or might be invalid index for particular range in the num array.
That's got to go nested in there. Query 0 and 2. Not 0 and 2. Hold on. So why is it... Okay. Queries is 0 and 2. Query is 0 and 2. Left becomes 0. Right becomes 2. So this is 0, 1, 0. So why is it not reducing the 0 by negative 1? Do you not reduce a 0 by into a negative? So in this case, if you reduce the indices 0, 1, and 2, so maybe if nums index I is equal to 0, we're going to...
Stromy says so if nums already contains a 0 you don't reduce it.
Yeah, that's what I'm trying to, that's exactly what I'm doing here. So if it's already a 0, I guess we don't reduce it, but it's not saying that anywhere in here, which is kind of goofy.
Stromy says only that 0.
Yeah, so if it's not equal to 0, reduce it, or if it's greater than 0, reduce it. Oh boy, not looking good. Taking forever to judge. Aha. So if you have a ton of queries, then interesting.
Stromy says, nice and always that colon haha.
So we need to figure out what to do if you have a ton of indices. So we need to save
Jamie says, hey bro, I just solved it. You might need to take a different approach due to TLE. This way, and says that's lead
Yeah.
code.
Yeah, it looks like we'll have to shake it up here, because it looks like they're wanting a case here with a ton of queries and a ton of numbers. So it's wanting something a little bit more efficient, time complexity wise. So the only thing I can think of, right, is if you reduce a value to 0, you don't need to basically do a loop over it again. Right, if you reduce a value to 0, you don't need to go back on another query over that value. It's technically done. So that would be a way to improve it again. So you can track scene indices, but your memory would grow really large proportionally to n for these scene indices, right? So that would be 2n memory. O of n memory. So then we're going over a range of values. Well, we know we need to go access every query, right? But if we've already seen a query and the section is all zeros, so I guess I could have like a set for queries, like scene queries, or a dictionary, a mapping, and then map a boolean of true or false to the value, saying that if the query is already have all zeros in it, it's true. Right. Let's think about it. Let's go. So this is 335. Let's say, let's talk about leet code 335. I am currently able to solve the problem, but I get a time limit exceeded for a mass amount of queries. I need to find a way to remove duplicate work. Let's discuss angles to go about this problem. Do not show code or spoil. You're on the right approach when hitting a time limit exceeded. Let's break down the current strategy. What kinds of work is being repeated? Start by profiling mentally or logging during test runs. Are you recalculating the same thing for multiple queries? Are you traversing the same structure repeatedly? Are you So could I loop through, I could do this, could I loop through the queries and identify how many duplicate queries there are for per index, then just mass reduce the index value from nums by that occurrence?
This way and says if I think that there are repeated query and queries, then we can make it one query and decrement each element in number count of same query until
Yeah, that's
0.
that's what I just typed in. That's literally what I just typed in. So let's think about this then. Let's say for query and queries, left equals right. I'm gonna say scene equals to a dictionary map of values. So we need to keep reference of scene values. So then we say for I in range left, right, plus 1, we're going to scene plus equals scene at index of I plus equals by 1 if I in scene, then we can say scene index I plus equals 1, else scene index I is equal to 1, right? And then we can say for key in scene dot for key value in scene dot items nums index key less equals value if return max or return sum of nums equals to 0, else return sum nums equals to 0. Oh, so we need that check on the 0. So if nums index key is greater than 0, nums index key less than or equals to value. Come on, show me the money. Come on. Ah, it's too slow. No.
This way and says no, say and says wasat.
Hey, how's it going? So for key value in scene dot items, okay, so
Jamie
this
says wouldn't worst case still be O, n squared, due to the second for loop where worst case you are still checking each index and query could be as big as the array.
yeah, so there's still definitely ways to optimize it still, right? But it's definitely better than our first approach. So then we just need to, right, what it's doing, what's going on here, giving us a problem, is that it's reducing the value into the negative. So we'll say if num's index key is greater than, if the num's index key minus is greater than 0, then we're going to subtract by the value. If num's index key, right, is less than 0, we're going to set num's index key to 0.
Wapiti says hello. Are these streams on Python Daily? Sorry for the random question, haha.
Yeah, I stream every single day. Welcome in, dude. I appreciate you for joining me here. Yes, this one's still pretty slow. Yeah, I still get TL. So we're doing repeated work by doing this second for loop. So it wants us to do this in linear time. We use a different array. Key value and scene items. So what if it says difference array. So what if I create an array out of the scene values and then subtract that array from this current array of numbers?
Zach says, if you're trying to learn to program, don't use LeetCode, man.
All right, let me mute it. So if we are highly suggest if you're new here to actually do some research onto the channel before chiming in about what we should and shouldn't do. Take a peek at what we actually know and what we do on the channel. So then, right, if we know all the counts, I wonder, can I build an additional array? Can I build an additional array given the indexes as the value, or the values as the indexes? So I wonder like this, like can I, instead of having scene be here, right, I want to do this. Like what if I do this? So if I have an array of 1, 0, 1, right, with 0, 1, and 2 being the indices. Okay, if I build an array based off of the counts, right? So this is going to go down by 1, this is going to go down by 0, and this is going to go down by 1. Based off on those queries. So let's do this. I have an idea. Let's try this. Okay, let's say for query in queries we'll say, we'll create an array here. So let's go like this. Let's do n is equal to the length of nums. And we want to create a copy array equal to 0 times n, right? Where we get zeros times the length of the numbers. Now for every query, what we're going to do is we're going to say for query in queries, left is equal to the query at index of 0. Right is equal to the query at index of 1. And we say for I in range of left to right plus 1, right, I'm going to go into my copy array at index of I and increase that value by 1. So we're going to get into copy by I plus equals by 1. Okay, so that's going to cycle through the query and increase proportionally there. So we're going to say, so that'll go through every query and make a list that will be proportional to all the reductions we need to make to the indices within nums. And then what we can do is just say result is equal to nums less copy, and then say get caught up on some chats here, hold on. I've been looking at your channel for a little bit. It's inspired me to do some live streams. I'm actually a CS grad, and I think daily live stream would help me practice. Yeah, dude, it's for sure helped me practice just by talking about this stuff every single day. No matter how little, just helps to further solidify the things and not let it leave my mind. So I can guarantee, I can 100% agree with you that just by talking, having to watch the streams back, edit the videos, interact with you guys on Discord, it all adds up into the compilation of the reinforcement of these topics, and that's what I really can attribute to my fast learning pace here. Okay. So copy plus equals 1. So then we return, we have the results here. Results equals nums minus copy. Now I don't want to sum results. So I wonder, we're already iterating over this range here. So I have another idea. I can loop through the queries and proportionally track the indexes of the queries along a dummy list of equal length to nums. Have all the values be 0 at first, then subtract dummy from nums to result in the 0 array. This is another clever and scalable approach and aligns closely with difference array pattern, commonly used in problems where you need to apply multiple additive subtraction operations efficiently. Your idea reframed. Let's create a dummy array called length equal to the proportional of nums. Initialize to all zeros, loop through the query, right? And for each index I, increment or decrement the dummy index I to track the net operations. Perfect. That's what we're doing. Once all results have been processed, apply the dummy as a batch operation. So then we can just say results index I, nums index I, copy index I. For I in the range. So then where can I put this result? This avoids repeat subtraction. So then what if I say that nums index I is equal to that one minus copy at that current place? So we just batch it down. And then return sum nums equal to 0. False. Crap. So if I save this rather as a result array, right? Nums equals to this copy. Nums index I minus copy index I equals to results at index I. Do I want to do anything with this value? If this value is... So I can create a new array for results, right? Or do I want to just update the numbers? Nums equals to nums less copy at this point in time. Unsupported operands types for list and list, so I can't subtract two lists. That's right. So then I have to subtract the individual index values of these lists. And that makes nums index I like so. False. Now I'm getting false no matter what. There's any false. So I'm going to take this, I'm going to show it here. I'm going to say, this is what I have so far. Just thinking here. Okay, so if we, very close. Yeah. So this just has to come outside of the loop because we need to have it happen at once, right? So we just have to say for I in like the range of 0 to n plus 1, nums index I less equals copy index I. We return that. I think that'll do it. List index out of range. So then, interesting. For I in the range of left plus right copy plus 2 plus 1. The difference or tally array. We say that the count is equal to 0. We say for I in the range 0 to n plus 1. Make n is equal to the length of the nums list. So then we say increase our count. Yeah, so we want to build a difference array that has 0 times n plus 1. Freeze left and right queries. Left plus 1. If the right plus 1 is less than n. So this would go for query left equals to 0, right, 1. We would say the difference array at index of left would increase by 1, but we need to check to make sure the right is in bounds. So if the r plus 1 is less than n, then the diff array at r plus 1 will decrease by 1. Why did I have decrease by 1? Because then you say for I in range of n. Now we can do the subtraction, right? Nums index I minus equals diff index I. If nums index I is not equal to 0, we're going to return false here, return true here at the end of it. So what are we doing here is we're creating right plus 1 This is my current code. What's wrong with it right here? I need to run a total. So I have to run a total out here, like a count. Another counter where I set the count or the total plus equals here, and then I reduce nums index I by the total at each step. Dang it. Left plus equals for left, right inquiries. We create a diff. Create a count. I in range of n. Total plus equals diff index I, nums index I minus the total. Return false. Let's see here. What do I have wrong with this still? What? Huh. This fails leak code. Why are we creating one greater than the length? No bounds check. Shoot. Huh. What's the problemo here? Why do I have this to be greater? I want it to be the length of n. Plus 1. False no matter what. Subtract 1 from the elements of L to R plus 1. Each query subtracts elements R plus 1. So n is the length of numbers. Diff is 0. Don't even need this. If num's index I less than total does not equal to 0, return false. If numbers index I does not equal to 0, so it's not less than or equal to 0, return false. It's greater than or equal to 0, return false, I mean. Num's index I minus total if it is not equal to 0, this is fails nums equals 1, 0, 1, and queries is 0, 2. So if the total I plus equals to diff, if it's less than turn no, come on. What the heck just happened? Prefix d equals 0 for I in the range of n. D plus equals prefix index I. Total plus equals diff index I. If it's plus, true here. He has plus. Error rendering component. It's false. True here. Expected is false. Go to Python. Stop doing that. Back to this. Java. No one wants Java. Start any queries. I don't get it. Why is this wrong? I feel like this is just the same. So prefix is 0 times 1. Perfect. For L and R in queries. Right? Left minus 1, a minus 1. And plus equal 1 on the left, on the right side. Why? How is this different than theirs? If end and plus 1. So length of n, so if we say this is times n, plus equals, this is minus equals. Minus equals current for I in the range of n total plus equals diff index I diff range. So they have that. I'm done. N plus 1 for LR in queries. L R. If R plus 1 less than n, then you do this. You say total 0 for I in the range of n, current if numbers index I is greater than current total return false. Alright, I'm done. This one's annoying. do you go one greater? Then he goes for a difference would be 5. All right, you guys, I'm done for today. I appreciate you guys hanging out with me for today. Please leave a like if you're new. Please subscribe if you're new. I stream every single day, me learning myself, teaching myself Python. Today we took a jump at learning and trying and starting the Khan Academy Calculus 1 course. I want to learn calculus more in depth and use Python to solve calculus related problems. So we are on unit 3 or lesson 3 of unit 1 here. We'll continue and probably do I want to do about 25 minutes every day of calculus 1 for the next couple of weeks. So at the beginning of every stream, we'll set a timer of about 20 or 30 minutes and do 20 or 30 minutes of calculus every day for the next foreseeable future. We'll probably finish this course up in a few weeks. As we do it every single day, we'll probably get through it pretty quickly. As well as continue on with our project in SpectroSim, where we currently need to write regular expressions to extract out that web scrape we did across that JSON. So as you can see for the compound toluene here, we're getting back some strings regarding its spectral information via that JSON parse that we wrote yesterday. And so we need to write some regular expression to actually parse now this individual string and extract out this information here. So things that we're going to want are like this guy. We're going to want kind of all of this kind of stuff. So I really appreciate you guys being here and hanging out with me today. Please leave a like if you guys are here and subscribe. I'll be back tomorrow. Please join the Discord. It's down in the description below where you can get access to a roadmap of all of my study resources from every book, course, and note that I've done. So feel free to check that out. And I'll see you guys later.